Stanford University.
All right, we started to explore entanglement. I had actually started to think about doing Bell's theorem tonight, but I decided not to do it yet. It's a complicated story, Bell's theorem. It's very lovely, but more important than the theorem itself is what it says. And so I want to get as much as possible tonight to what it says and what entanglement has to tell us about the nature of systems. Sometimes people say the nature of reality. I don't like the word reality. I think it's misleading. Okay. In looking on the internet at the messages you guys send back and forth, they're very interesting, and many of them have some very interesting points in them. There's a terminology which I would discourage, at least unless you know what it means with greater precision. And I've seen this all over the place. People say entanglement is when two quantum systems share the same share a state. I've never understood what that means, to share a state. Quantum systems have states. If they're composite quantum systems, they have states. You can say that a quantum system, a pair of quantum systems, when they make a given quantum system, share a state, if you like, but it just means the state of the composite system. The important idea about entanglement is not so much that systems share a state, that they always do. The important thing is that they are not described by a product state. A product state being a state in which the wave function of the system, and we'll talk about have we talked about wave functions very much? I don't think we have. Let's begin by talking about wave functions, and then I want to move on to the concept of a density matrix. This will make it much easier for us to think about entanglement. First of all, the notion of a wave function. A wave function may or may not have anything to do with waves. The concept grew historically out of the quantum mechanics of particles and the relation and the probability description of them in terms of waves. But the logical concept of a wave function is one that you can apply to any quantum system, and in general it doesn't have to do with wave motion of any particular kind. The basic idea of a wave function is the following. You have a quantum state. Let's call the quantum state capital psi. I'll use the letter capital psi to denote a generic quantum state of a system. I think previously I've been using A's and B's, but I'm going to start using psi as a generic quantum state for pretty much any system. And also I have a basis system. The basis system is typically labeled by a collection of eigenvalues of something. It might be labeled by one or more variables. If there are several commuting operators in a system, you can specify simultaneously the eigenvalues of more than one thing. And in many cases, you'll want to do that. And the basis vectors in those cases are labeled by a collection of observables or a collection of eigenvalues of perhaps several quantities. I'll give you an example. If you're talking about the motion of a particle, then the x and y and z coordinates of the particle are commuting variables. The things that don't commute are the components of momentum with the components of position. I know we haven't done this yet, but on the other hand, the three components of position all commute with each other. That means they can be specified simultaneously. A useful basis for studying the quantum mechanics of a particle is a basis which is labeled by the 3 coordinates of the particle. I'll wait for... yeah, I'll give her a hand. All right, so we have a basis, and the basis is labeled by a collection of eigenvalues. Let's label them. Let's don't have a decent pen. All right, A, B, C, however many commuting variables there are that need to be specified in order to specify a system. And the inner product of the basis vector with the state of the system itself is called the wave function. In fact, we can write that psi, since these objects here form a basis, we can say that this is a sum. I still don't have a decent pen. A little bit better. A sum over the basis vectors, which means a sum over this collection of eigenvalues, a, b, dot, 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 of the inner product of the basis vectors with the state vector times the basis vectors. We've written this kind of equation down before. What it says is that the expansion coefficients that you use to expand a vector in basis vectors are just the inner products of the vector with the basis vectors. This object is called the wave function right here. And it's a function of the A's, B's, and C's. So let's give it a name. Let's call it little psi of A, B, C, and so forth. It's called the wave function, and it's defined in such a way that the state vector psi is equal to the sum over A over all the indices which it takes to specify the basis times psi of A, B, and C, and so forth. Psi of A, B, and C, of the coordinates of the, what the coordinates, an example, if we're just talking about a single spin, then a complete set of commuting variables necessary to specify a vector is, for example, just sigma z, the z component of spin, and then psi would just be the probability amplitudes for the spin to be up or the spin to be down. It would be a function of one variable. That variable would take on the values up and down. If we had 2 spins, then we would label a basis of vectors with ups and downs for one spin, ups and downs for the other spin, and it would take 2 labels to label a state vector, not just one. The 2 labels would be the labels of the 2 spins, and that's all we're talking about here. It might take multiple labels to label a basis vector, and if so, just display them here, and then by definition, as pure definition, the wave function of the system, you can think of it 2 ways. You can think of it as the set of coefficients, the set of coefficients that you use to expand an arbitrary vector in terms of the basis vectors, or you can think of them as the inner products of the state vector with the basis vectors themselves. That is called the wave function, and Schrodinger's wave function is a special case of it, which we will not get to at the moment, but it is a special case of it. Question? Okay, so if you know the wave function of a system, you know its state vector, and you can compute all sorts of things. You can compute expectation values and all sorts of things. Yeah.
This looks a little like a Fourier transform in some basis. Is a Fourier transform?
Yep. It is a Fourier transform for the case of position and momentum. If yes. Yeah.
So in that case, you could go back and forth.
Well, no, the Fourier transform is going back and forth between different basis sets. Okay? Here I've chosen a particular basis set. Supposing I wanted to use a different basis, instead of sigma z, sigma x, then I would have to transform these wave functions somehow. They look different in the x basis, and that's the analog of Fourier transform. Okay. Now I want to introduce a concept called the density matrix. If we have just a single system, this is the way we think about the state of the system. Oh, let's talk about expectation values. Let's talk about expectation values. Supposing we have some observable. Let's call it L. Let's call it L. It's some observable. And it has matrix elements. What do matrix elements mean? They mean, if this is a basis vector, I won't bother writing out multiple labels. Let's just put one label there to summarize all the labels. And another label over here, a prime. These are called the matrix elements of the observable. Okay. The matrix elements of the observable acts on a basis vector, and then you project it onto another basis vector, and that's called L, I suppose, A prime A. Just notation. Okay, now supposing I want to calculate the expectation value of L in a state whose wave function is psi. Let's see how we do that. We take psi. I'm going to, as I said, I'm just going to restrict myself to a single A here, but the same thing would hold if there were multiple A's. All right, so what do? We take the state vector on the left, the ket vector. The ket vector, maybe we should write out the ket vector here. Sorry, the bra vector. The bra vector, this is the ket vector. The bra vector is the sum over A and B. But you know, I want to use different indices here. I want to call them A prime and B prime. They're being summed over, so it doesn't matter what I call them. I just don't want to confuse them with these. And then we're going to have bra vectors, ABC, or times, now do I put psi here? Psi star. So exactly the same kind of expression for the bra vector, except complex conjugated coefficients. Good. Now let's calculate psi L psi. That's the expectation value or the average value of L in the quantum state psi, and we do it just by plugging in. The left bra vector here is the sum, just a single index, A prime psi of A prime. That constructs the bra vector. The ket vector, I will have to write another sum, a sum over A of psi of A times A. Summing on A turns this into the ket vector psi, capital Psi. Summing over A prime turns this into the bra vector, the corresponding bra vector. And in between, we sandwich L. All right. Now, this, somebody please correct me. What did I write wrong? Psi star. All right, we take the psi's and the psi stars out of the expression. They're just numbers. And so the whole thing is a sum of A prime and A, psi star of A prime, psi of A, times the inner product or the sandwich A prime LA. That's exactly the matrix element of L between A and A prime. So that's L. Which one is it? A prime A, I think. And this reduces every expectation value to a calculation in terms of wave functions, a psi, always a psi and always a psi star, times a matrix element of the observable that we're interested in. All right, so this is a basic formula for the expectation value of anything that we might be interested in. Okay. Basically, all of quantum mechanics is contained in there. The expectation value of everything in the world, that's just about everything we ever may want to be interested in. And so let's put this equation over here and keep it over here. Now, supposing we have a composite system composed of two subsystems. Let's call them Alice's and Bob's subsystems. All right. Alice has control of one of them. Bob has control of the other. And maybe even there are times when they don't have control of them. But we'll just call them two subsystems, Alice's and Bob's. Then, and in fact, let's use A now to represent a complete set of observables for Alice's subsystem. Everything that Alice needs to know in order to specify a basis for her subsystem, and B are the set of variables for Bob's subsystem. When we talked about spin, I think we called Alice's variable tau and Bob's variable sigma, if I remember correctly. But these are a complete set of things, a complete set of variables for Alice, and this is a complete set of variables for Bob. Alice's states for her subsystem would look like this. Bob's would look like that. Maybe we want to use a different notation so we don't wind up confusing the two vector spaces. But then there's the composite vector space. The composite vector space is the vector space describing the composite system, and that has a basis which consists of an A and a B. When A runs over all its values and B runs over all its values, we have a complete basis of the combined system. Okay, so now let's talk about wave functions of the composite system. Again, we have a state vector. The state vector psi is a state vector in the composite in the tensor product space. The space made by tensoring producting A's and B's together. It has as its basis vectors a basis vector from A and a basis vector from B. And now I want to define in the same way the notion of a composite wave function. So what is it? It's just the inner product of psi with the basis vectors. And what is it a function of? It's now a function of two sets of variables, or two variables, psi of A and B. Different B here. Okay, here it is. It's a function of the variables of the two subsystems. It depends on two of them. Okay, so that's the wave function. Now we have notion of a wave function of a composite system. And let's talk about observables of a composite system. The observables of a composite system, first of all, among those variables are the ones which would describe the separate subsystems by themselves. So let's suppose that L and M are two observables, one of them having to do with Alice's subsystem, Alice, and the other one having to do with Bob's subsystem. I could call them L sub A and L sub B, but I won't. I'll call them L and M. How do we represent observables acting on the composite space of states? The answer is simple. The operators associated with Alice's subsystem act on Alice's piece of the state vector and leave Bob's piece of the state vector unchanged. That's what we did when we did spins. We said Bob's sigma matrices acted on his half of the wave function, or his half of the basis vectors, and were completely passive, or Alice's piece of the state vector was completely passive, just bypassed by these operators. So what that says is that Alice's observables are matrices. They're matrices that can be written as L of A prime B prime, just like L here, has a primed variable and an unprimed variable, but now the single index is replaced by two indices, and A and B. What does this correspond to? This corresponds to the sandwich A prime, B prime, L, AB, whatever this stands for. But L only belongs to Alice's space of states, only belongs to Alice's system. So the question is, what then do we say about this matrix here to indicate that it has no effect on Bob's variables? The answer is simple. We make it proportional to the identity matrix in Bob's variables. The identity operator in a space is the operator whose matrix elements are the Kronecker delta symbol. That's the identity operator. And the identity operator on a subsystem does nothing to that subsystem. The identity operator simply gives the same vector back. In other words, if you apply the identity operator, it does nothing. But now what we're doing is applying the identity operator on Bob's half of the system, but the observable that's supposed to be associated with Alice's half of the subsystem is represented by the same matrix that she would have used had she not even known about Bob. Had she not even known about Bob, she would have used the matrix L, A prime, and A to describe her observable. How does she describe it in the bigger Hilbert space? She says it does nothing to Bob's variables, and so it's just the identity matrix in Bob's half of the space. That's Alice's variables. We could say the same thing about Bob's. M of A prime and B prime and A and B is just equal to the Kronecker delta of Alice's variables times the matrix that Bob would have used to describe the subsystem had he not known anything about Alice. Okay, let's prove some things about this setup here. First of all, let's calculate expectation values of Alice's variables in a product state. A product state is one in which the two systems are not entangled with each other. And let's see what we get. What would you expect to get if you had an unentangled state describing Alice's and Bob's subsystems, and you considered the expectation value of Alice's variable? You get exactly what you would have gotten had Bob not been there altogether. So let's check that out. What do I mean, first of all, by a product state? I explained what a product state was, but now let me explain what a product state is in the language of wave functions. It's very simple. It means that the wave function is a product of two wave functions, one for Alice and one for Bob. That's all it means. A product state is one whose wave function psi of A and B, Alice's and Bob's variables, is just a product. So let's see, how shall we denote that? Let's call it, well, let's just call it psi Alice of A and phi Bob of B. It factorizes. It's a product of two functions. It's a function of two variables, but it's a product of two functions, each of one variable. It's pretty clear that if it factorizes like this, then Alice can think of this as the wave function for her subsystem, and Bob thinks of this as the wave function for his subsystem. Okay, let's calculate now Alice's expectation value of L if this happens to be the wave function. So what do? We first take psi, we're going to make a sandwich. We're going to make a sandwich with a psi star on one side, a psi on the other side, and L in between. All right, so psi star, that's psi star of Alice of A prime, phi star Bob of B prime. This is, where do we write it? There. That's the complex conjugate of the wave function as a function of A prime and B prime. What next? Next, we put in to the sandwich L of A prime, B prime, A and B. It's a matrix, one entry here, one entry here, but it's simple. It's just L of A prime and A times delta BB prime. Okay. And then we close it up with the other half of the sandwich, which is this up here, psi A of A, phi B of B. And we sum. As always, we sum over everything in sight, A prime A, B prime B. That's the rule for calculating an expectation value. So what do we get? First of all, the delta BB prime, that tells us to set B prime equal to B. So let's do that. First off, let's do that. I'll just erase. Set B prime equal to B. All right, I'll let you write down your notes if you want. Set B prime equal to B and remove the Kronecker delta. Now B is equal to B prime. Now notice, the only thing that depends on B is phi star B and phi B. The sum over B prime was done when I set B equal to B prime. And now there's a sum over B of phi star phi. What does that give? 1. Under the assumption, of course, that Bob's wave function is normalized. Under the assumption that Bob's half of the wave function is normalized, so that his total probability for all his measurements he could do is 1, then sum over B of phi star of B times phi of B is just 1. And what does the whole thing reduce to? The whole thing reduces to exactly what's up there. We can remove the phi's, take them out, put them down here. That sum is just 1. And the rest of it is just exactly what's up on the top of the blackboard there. In other words, in a product state, the expectation value of any of Alice's operators are exactly the same as if Bob wasn't there. And it doesn't matter what Bob's wave function is as long as it's a product. What about one of Bob's expectation values? What would happen if we stuck a Bob operator in there? Well then, instead of the Kronecker delta of B's, let's go back. We have B and B prime, B and B prime, B and B prime, B prime over here. And instead of L and L, we would have M of B and B prime, delta A prime. And now we would set A prime equal to A, sum, that would again give us 1, and we would get the same, we would get basically the same thing that I wrote up here. Bob, except it would be Bob's wave function, phi star Bob of B prime, M of B prime B times phi Bob of B, which is exactly what Bob would have done had he not known about Alice. So product states are really just that. They're states in which one party just doesn't know about the other. There's no correlation. There's no information in one of them about the other. We can say a little bit more about correlation. Let's suppose now that we were interested in the product of an Alice variable and a Bob variable. We're interested in the expectation value of L times M. Let's see what we get. expectation in the product state, strictly product states for the moment. We go back up to here, and now instead of writing MB, is this BB prime? This should be B prime. Instead of delta of A and A prime, if we're taking the product of L and M, then what do I put here? L. If I'm interested in the operator which represents the product of two variables, one for Alice and one for Bob, instead of putting the unit operator over here for Alice, I will simply put in Alice's operator. Not M, Alice, L. Now this just factorizes. Let's look at all the A dependents. Here's A dependence, here's A dependence, here's A dependence. That factorizes. That's completely separate from the B dependence. I could take everything with a B dependence and put it on one side, everything with an A dependence and put it on the other side, and do the A and B summations independently. Can you see that? All right, let's write it out. It's sum of A prime A, B prime B of psi Alice star of A prime L A prime psi Alice of A, all times phi Bob star of B prime M of B prime and phi of B. The sums can be done quite independently. We can put this sum over here. Same thing. I haven't changed it. We're summing over everything, B's and A's. And we see that what we get is just the product. We get the product of the expectation value of L times the expectation value of M. Not surprising. If we have a product state and Alice does her measurement and Bob does his measurement, and we then come together and compare the measurements and ask what was the product of the measurements, the expectation value will just be the product. The expectation value of the product operator will be the product of expectation values. And we can write this way. Let's write it in a form. It says for product states, for what's called product states. The expectation value of L and times M. Now remember, L belongs to Alice, M belongs to Bob, and they operate in different halves of the system. The expectation value of L times M is just the expectation value of L times the expectation value of M. Now, is this something that we expect to always be true for every state? That the expectation value, in fact, even in classical probability theory, if we have a probability distribution for two variables, in general, is it true that the average of the product is the product of the average?
Only if the variables are independent.
Which means what in terms of the probability distribution?
Exactly what you've written there.
It means that it factorizes. It means that the probability distribution is a product of two probability distributions. Right. Well, what if it's not true? What if the probability distribution does not factorize? Then this quantity here, the difference between the average of L times M and the product of averages of L and M is called the correlation between L and M. It's called a correlation, and it is a measure of how much these variables are correlated. We'll see some examples. This is called the correlation, and whenever there is anything in the system, an Alice variable and a Bob variable, whose correlation is not zero, that's an indication of entanglement. If you can find any pair of variables, one of Alice's and one of Bob's, such that the average of the product is not the product of the averages, then you're experiencing entanglement. I think we did an example last time. We took what I called the singlet state, which was up, down, minus down, up, over the square root of 2. This is psi, and this is not a product state. And in this state, we took the expectation value of Bob's variable sigma z. We took the expectation value of Alice's variable, which I think was tau z. Do you remember what these were? What's the average value of Bob's variable? Let's say the first entrance here, the first entry stands for Bob. Here's Bob, Bob, here's Alice. What would you guess in this state the average of sigma z is? Not the state, but the combined state. No, 0. Why is it 0? Because it has as much probability of being up as being down. Has probability 1/2 to be up and 1/2 to be down. So the average of Bob's variable is 0. I think we worked that out last time. What about Alice's variable? It's also up as much as it's down. Okay? It's also expectation value is 0. What about, all right, so first step, both of these are 0 in this case. What about the product? What about the product of sigma z and tau z? What's its average value? Well, we worked it out last time. We got an answer. Anybody remember the answer? -1. -1. But you can just look at this thing, and you can say in both vectors here, the spins are opposite. So in either case here, the product of the spins is -1. It's pretty clear that this whole thing is an eigenvector of the product, because on either vector here, the product is -1. Act with sigma z. Act with sigma z, you'll get, you know what will happen. So it'll just change sign. So yes, this has the product of the sigma z is equal to 1. -1, excuse me. So they're entangled. In fact, in this case, they're what I'll call maximally entangled. They're very entangled. If you can find any pair of variables which are correlated in this form, the quantum state is entangled. Do you remember now, here it's completely obvious that the average of sigma z is 0 for just the reasons that I said. For sigma z and tau z. Up appears as much as down for Bob, and down appears as much as up for Alice. And so it's clear the average is 0. What about the average of sigma x? Do you remember? It's 0. But that's not obvious, is it? That's not obvious. But we did it last time. Go back to your notes, and you'll discover that not only is the expectation value of sigma z 0, but sigma x is also equal to 0, the average. On the other hand, you'll also find that the product of Bob's sigma x and Alice's tau x is again equal to -1. So the sigma z's and the tau z's are correlated. The sigma x's and the tau x's are correlated. And what about y? Same thing. Same exact thing. You can work that out. We know what these operators do. You can apply them to the states and calculate what their expectation value is. So this state is a highly entangled or a highly correlated state. Being correlated and being entangled are basically the same idea.
Question?
Yeah.
In the general case, if you flip the L's and the M's around, it's equal to each other. In other words, flip the L's and the M's, LM minus bracket L, bracket equals ML minus, is that, what I'm saying?
No.
Okay, just flip the L's and the N's.
Oh, yeah.
That's people, right? In the
Yeah,
general
sure.
case. Sort of-
All right. There's a point there, which I may not have mentioned. All operators associated with one system commute with all operators associated with the other system, so it doesn't matter in which order you write them. That's independent of whether the system is entangled. Doesn't matter which order you write them.
Excuse me,
Yeah.
I guess I'm missing something. When you wrote that down, you showed us that if you have a product state of where L is a state in Alice's and Emmett's.
Yeah. Then this is equal to 0.
And that's equal to 0.
Yeah.
What does LM mean if it's, I mean, you've got it written up there, isn't that a product state?
This? No.
What is it in
The
general,
state is, these are the states. These are the observables.
right?
Right.
Doesn't that LM being a product state, L?
No, L's and M's are not states. Yeah, there are size in here. This is a statement about the state vectors. Right. Okay. One other point is worth just noticing. When I say things are correlated, that the spins are correlated, I mean it. What I mean is that you can learn something about one variable by looking at the other. If you know that this is the state, if you happen to know that this is the state, then if you measure Bob's variable and you find out that it's up, then in that component of the state, which is the only one that's left after you measure Bob, Alice is down. In a product state, you learn nothing about one system by measuring anything about the other. In a highly entangled state, you learn a great deal about one system by measuring the other one. Okay, that's what entanglement means. On the other hand, it may also follow, and it may also be true, that in a highly entangled state beforehand, if you happen to know the state, you may know very little about each individual piece. For example, in the singlet state here, there is, what is the probability that Bob's variable is up? 1/2. What is the probability that Bob's variable is down? 1/2. So in this state, knowing everything about this state, you still know nothing about whether Bob measures up or down if he does a measurement. Curious. You know nothing at all about whether Bob measures up or down. You know nothing at all about whether Alice measures up or down, but you know everything about the product of them. That if Bob does his measurement, Alice does her measurement, and you compare them afterwards, every single time, if this is the state that you put the system into, the product will be minus. So this is an example of this odd thing in quantum mechanics that you can know everything about a composite system and know nothing about the pieces. That's what this is telling you. You know everything, or when I say you know everything, I mean you know as much as quantum mechanics allows you to know. This is the state of the system. You're not going to do any better than that. That's all there is to know about it. What you know about it is that sigma times tau, whether it be sigma x or tau x, this is true for the x, y, or z components separately, that the product of Alice's variable and Bob's variable is -1. That's a lot to know, but it's not as much as you would know classically. Classically, if you knew everything about a system, you would know everything about the constituents, as well as things that you could measure about them that you could combine together. In quantum mechanics, you can't know, or either you can say you can't know everything, or to the extent that everything is everything you can know. In this case, you know everything about the combined system, and you know nothing about its constituents. That's the really odd thing about entanglement. That's the extremely odd property of quantum mechanics, that it allows such nonsense.
Wouldn't that just mean you can't separate, decompose the system without destroying information or something?
Yeah. Yeah. Yeah, it does mean that.
When you write LM, I'm a little confused. Is that measure M and then measure L?
No, no, no.
It's the product of L and M.
All right, let's be very clear. Let's be very clear. The mathematical operation of multiplying a state vector by an operator is not got anything to do with the actual physical act of measuring it.
I know, but the syntax looks the same.
I'm not sure, the syntax is not the same. I'm not sure what syntax means. I assume it means the words.
It just means, how do I interpret LM on the board? That's all. The product of the operators.
Yes, yes, it means you act first with M and then L.
Okay.
Yeah. Yeah. But it doesn't mean that you've measured them. It means this is just a mathematical thing. Right. It's the same is true in classical mechanics. I can multiply the momentum of something by the position of something else. That doesn't mean I measured them just because I've multiplied the two things together. Physical act of measurement, it's not the operators which act on the states, it's the detectors or apparatuses which act on the system. So in words, when you do a measurement, a detector or an apparatus acts on the system and gives a result. In the space of states, a operator acts on a vector, not a detector acting on a system. Quite different concepts. Yeah.
Before we make a measurement on an electron, unless we already know how it's been prepared, which is a special case where in that case we can describe the state as a linear combination of basis vectors. But before we make a measurement, we might know nothing about it. We might know a little bit about it, but no matter how much we know, will have to be expressed in terms of probabilities, not in terms of the vectors.
Yes.
So in the case where there's a correlation between two electrons, and let's say it's not a pure correlation, it's a partial.
It's not a product.
It's not a product, and it's not a purely entangled state. It's somewhere between.
It's not a what?
A siglet state, for example.
It's a somewhat entangled state.
Exactly. So if then after we make the sigma measurement, and we want to describe the tau electron, we would still have to describe tau in terms of probabilities. We wouldn't be able to specify it in terms of a combination of.
Okay. I'm not exactly sure what you're getting at, but maybe this will help. If we have the quantum state of a single spin, let's suppose somebody told us what the quantum state of a spin was. All right. Then for any quantum state, there is always an observable, in particular, some component of sigma, which is definite, which is predictable. Every part, that's obvious for the states up and down. It's obvious for the states left and right. For the state up, if you measure sigma z, it's definite. If you know that the state is right and you measure sigma x, it's definite. This is more general. Given any quantum state whatever of a spin, there exists a direction, this you can prove, that there exists a direction for which the spin is definite. Okay? Curiously, when you combine the system together into an entangled state like this, there is no direction in which the spin is definite. In fact, there is no direction, sigma x, sigma, for one of the spins. Each one of the spins, either Alice's or Bob's, has average value 0 in every direction. No matter what direction you pick, x, y, z, or anything in between, the average of the spin, of Bob's spin, in this state is 0. So here's a quantum state in which Bob can say nothing whatever. He can know the quantum state fully, and as I said, has equal probability for up and down in every direction. I'm not sure if that's what you're addressing or not.
Well, my question in a nutshell is if we have a partial correlation.
Oh, partial, okay.
Correlation is somewhere between 0 and 1.
All right, so we put a big number here and a small number here.
Yeah, so we measured 1, and then the other could be expressed as various probabilities of sigma x and sigma y.
Yes, 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 yes. We can calculate all the probabilities. We just calculate them. Yeah. Okay.
Could you remind us the physical?
What is that?
For a singlet state?
Say it again.
What would be an example of a physical experiment corresponding to a singlet state?
Good, good, good. That's an important, obviously an important question. Another way to ask it is, how would you prepare a system in the singlet state? All right. All right, I'll tell you something about the singlet state. The singlet state has the property that it's an eigenvector of a certain operator. It's an eigenvector of many operators, but in particular, it's an eigenvector of sigma x tau x. You can prove it. It's actually an eigenvector of sigma x tau x. It's an eigenvector of sigma y tau y. And it's an eigenvector of sigma z tau z. What's the eigenvalue for each one of these? -1. And the eigenvalue is the same for all of them. That means that it's an eigenvector of any combination of these with eigenvalue -1. Any one of them acts on the singlet state, gives back minus the singlet state. Any combination of them will give back minus the singlet state. So in particular, if I take this object here, the singlet state is also an eigenvector of this. Now, this is a funny thing. Alice and Bob can't easily measure this whole quantity here. Why? Because Alice can't measure tau x and tau y simultaneously. By separate measurements, this would be hard to measure. Can't be measured by separate measurements. Why? Because no separate measurement can measure tau x and tau y at the same time, or tau z at the same time. But this object is a perfectly good Hermitian operator, and there must exist a way of measuring it. But more to the point right now, there's a way of preparing a state which is an eigenvector of this. Now, what state? The singlet state. The singlet state is an eigenvector of this object with eigenvalue -3. It's an eigenvalue of this one with -1, this one with -1, and this one with -1. The whole thing has eigenvalue -3. But the point is, the eigenvectors of this product, or the sum of products here, include the singlet state as a particular one. You can also write this as just sigma dot tau. Sigma x tau x, sigma y tau y, sigma z tau z. That, if these were ordinary classical vectors, you would write it as sigma dot tau. Now, if you take two electrons, each one has its spin, and they're very, very far apart, they don't interact with each other. There's no energy associated with the interaction between them. But as you bring them together, there are all sorts of energies. One energy, for example, is just a Coulomb energy between them, product of the charges. There is also an energy associated with the spins. And one of the terms in the energy associated with a spin is just a dot product of the spins. If the spins are aligned, you get, if this is aligned, you get one value. If they're anti-aligned, you get the other value. And so sigma dot tau is a piece of the Hamiltonian of the two-spin system. In the singlet state, it's minimum. There's three other states called the triplet state in which it's maximum. So the energy is lowest in the singlet state. The spins are trying to get anti-aligned with each other, but in every direction, not just the z direction, in every direction, and they eventually compromise on the singlet state. So you'll have two energy levels associated with the spin of an electron. These two energy in hydrogen, or in positronium even better, in positronium you have the aligned and anti-aligned spins, and they have different energy levels, singlet, triplet. if you bring two electrons together, then any state can be written in terms of the singlet and triplet states. Even the product state can be represented as a sum of singlet and triplet states. What happens when you bring the electrons together after a period if they're in the triplet state with a higher energy? What happens to higher energy states after a while? They emit a photon and go to the lower energy state. So if you take two spins, which may be in a product state, and you bring them together and wait a long time, a photon may or may not be emitted. If the system is in the singlet state, no emission. If it's in the triplet state, it emits, gives off a photon, and winds up in the singlet state. So this would be a way of preparing the system in the singlet state. You just take the two electrons and wait until they radiate a photon, wait long enough. They either do or don't radiate the photon, but if you wait long enough, you'll know that it's in the singlet state. All right, so that's a experiment. That's an experiment to another way. Another way. Now this one is very, very far-fetched, extremely far-fetched. The energy in the singlet state is less than the energy in the other three states. There are four possible states altogether, four possible basis states, singlet and three triplet. The energy of the singlet is lowest. So you just take your composite system and you put it on a scale and you measure its mass. Mass is energy. When you've measured its mass, you've measured whether its energy is the energy of the singlet state or the triplet state, and that constitutes a measurement, or constitutes a preparation device or a measurement of basically this variable, but if you like, the difference between singlet and triplet. So yeah, there are ways of preparing systems in the singlet or triplets in the singlet state, or ways of, in fact, if you bring the systems together and you wait a while, it's very difficult to have anything but the singlet state. Then once you've made that singlet state, if you grab the electrons without turning their spins, if you grab them somehow in a way that doesn't put any torque on their spins and pull them apart, you now have two separated electrons, for example, in the singlet state. So it's not a terribly hard thing to do.
With the speed that you can actually assign an energy to the entanglement?
Yes, in this case, yes. In this case, yes. But that's, well, what you can say is the lower energy is certainly entangled. The lowest energy state, the one that it seeks when it to get to by, and it doesn't have to be radiating a photon. Any mechanism by which the system can lower its energy, emitting a phonon or doing interacting with a crystal lattice or anything to lower its energy, will leave it in the singlet state. So, and I think the right thing just to say is that the lower energy state is entangled. That's almost always the case. That the states of lowest energy are highly entangled between systems. Okay, so next question. Is there a measure, is there a quantitative measure of the degree of entanglement? Is there a way of taking a state and determining whether it's entangled and to measure how much it's entangled? Okay. That brings us to a concept called the density matrix, which I'm probably going to, it's getting later than I thought, so I want to go over this a little quickly, but I think we can do it. Let's define an object called Alice's density matrix. Alice's density matrix is a quantity which, even in an entangled state, is as complete a description of Alice's system for the purposes of Alice's measurements as Alice can ever get. It's not a wave function. If it was unentangled, the wave function would be the best description she could have. But for an entangled system, you cannot extract out a wave function for either piece of the entangled system. The best you can do is something called the density matrix. We actually had it up here. Let me go back to it. Let's talk about all of Alice's experiments that she can do without measuring anything about Bob's electron or Bob's system. Let's imagine that they've separated their systems. Bob has his, Alice has her, and Alice can do all the experiments she likes and measure any one of these L observables. L standing for Alice. Okay. How does she describe all the possible expectation values of everything that she can ever measure? So we had a formula up before, and I'm going to rewrite it. Expectation value of L is psi star of alpha, let's see, what was it? Alpha prime, beta prime, or A prime, B prime. This is the combined system. We're going back to the combined system now. L A prime A psi A B, but we set B equal to B prime. Or if we like, we can leave the B prime here and put a Kronecker delta of B and B prime. This is one of Alice's variables. And so as far as Bob goes, it's just the unit operator. It does nothing to Bob's piece of the wave function. And that just says stick B equal to B prime. OK, look at this quantity right over here. Let's take L on the outside. Let's take L of A prime and A out there. Isolate it off. We have to sum this over B. We sum over everything. We sum this over B. And here's a quantity right here that depends on A prime, A, and it multiplies something else that depends on A and A prime. But it doesn't depend on B. We've summed over B. Once you've summed over B, it doesn't depend on B anymore. So this object over here is a function only of Alice's coordinates, A and A prime. It, of course, to calculate it, you may have to know more about the wave function, but once you've calculated it, that's all that Alice ever needs to know to calculate anything about her half of the system. So let's give it a name. It's the sum over B, psi star of A prime B psi of AB. It doesn't depend on the B degrees of freedom at all anymore, Bob's degrees of freedom. It's called the density matrix, and it's a function, it's a thing which depends on A prime and A. It's a matrix. It's a matrix. It has two entries. Any matrix can be thought of as a function of a row and a column. This is a density matrix. And if we know the density matrix, it doesn't matter where it came from. It doesn't matter what Bob's state was. If we know row, then we know that the expectation, let's write the formula, the expectation value of L is equal to the sum of row of A prime and A, L of A and A prime. I think I have one of them backwards. It doesn't matter. So Alice, if she knew this density matrix, could forget about Bob completely and say, I know everything that there is to know about my subsystem, and here it is. Okay. What is row of A and A prime if we start with a pure state? Supposing we started with a pure state. Are you getting exhausted? Well, this is quantum mechanics for you. Sorry, buddies, but this is it. I can't make it any easier. This is as easy as I can make it. All right? You got to sit down with it, and you got to go through it and penetrate it. But I'll do my best. Okay. This is the notion of a density matrix. What if psi is a pure state. What can we say about this density matrix? So let's go back and see exactly what it says. If psi is, what if psi is a product state? If psi is a product state, it means the wave function factorizes. So let's go back. Here we are. Here's the density matrix. The wave function factorizes into a, this is B prime. Yeah, that's right. That's correct.
Your density matrix, your sum is over A prime and A, so it's a double sum.
Not in the density matrix. In this one, yes. It's a double sum. It's a double sum, but it only involves rho. So let's erase this for a moment and see what we learn about this creature called the density matrix if psi is a product vector. It must have a special form somehow. So let's say that psi is a product of Alice's wave function times Bob's wave function. I forget which one is which now. Was psi Alice or was psi Bob? Psi was Bob? Psi is Alice. Okay, it doesn't matter. We'll just change them now. All right. So the complex conjugate here is Alice's wave function times, this is not the wave function of Alice. This is the wave function of Alice's spin, incidentally. But I'll call it Alice's wave function. Alice's wave function times Bob's wave function, the complex conjugate. And then we multiply that by the non-complex conjugated thing. Let me put them in the opposite order. Phi of B. Notice we've identified B with B here. It's not B and B prime. And this is prime psi A. Each one of these factorizes. This factorizes into a function of A prime and B, and this one into a function of B and A. And now we sum over B. What is the sum of B of phi star phi? 1, right? Okay, so now we can take this out and throw it out. And here's what we find. We find that for a product state, only for product state, that rho is simply made up out of Alice's half of the wave function without any regard to Bob. She doesn't need to know anything about Bob. This is not too surprising that she didn't need to know anything about Bob. After all, it is a product wave function. And the density matrix is just a product of the complex conjugate of the wave function with the wave function itself. Two different A's, though, an A and an A prime. What can we say about a matrix like this? Let's call this matrix, let's call it, I think it's actually rho of, let's call it rho of A and A prime. Just call it rho of A. I've switched the order, but that's just a definition. Let's take this rho, it's a matrix, and act with it on a column vector. How do you act, if you know the components of a matrix, how do you act on a column vector? So let's suppose this is a matrix. Here's, yeah, row 1, 1, just a second, row 1, 2, so forth, row 2, 1. We make a matrix out of it. Yeah.
Do you want to erase that summation sign there on the far?
Yeah, I do. Good point. Excellent. All right, so we have rho. It's made up out of Alice's wave function. And I maintain that this density matrix, thought of as a matrix, has an eigenvector. I maintain, moreover, that it has one and only one eigenvector with non-zero eigenvalue, and that that eigenvalue is +1. Somebody say right? Good. Okay, let's prove it. I'll tell you exactly what that eigenvector is. It's psi A. It's psi itself. It's psi itself. So let's check that out. Let's multiply this by psi of A prime, in fact, and sum it over A prime. This is matrix. This is the process of multiplying a column vector by a matrix. That's the way you do it. You write down the matrix, you write down the column vector, and you sum over the element between them. Okay, let's see if we can see what we get. Oh, this is the action of rho on psi. Okay, so let's do it. Rho, here's rho. Now let's multiply it by psi of A prime. And now let's sum over A prime. What do we get? Psi star of A prime times psi of A prime summed over A prime is 1, right? So it all comes out to just be psi. So this is psi. What does that tell you about eigenvectors and eigenvalues of the density matrix? It tells you that the original wave function is an eigenvector of the density matrix with eigenvalue plus 1. Let me prove now that all vectors perpendicular, there are n minus 1, if the dimensionality of the space is n, then this is one eigenvector out of n, which has eigenvalue 1. Let's take any vector now which is perpendicular, which is orthogonal to psi A, to Alice's wave function. Let's call it psi A tilde. Tilde now means it's orthogonal to the original Alice's vector. Now what is this inner product? 0, right? So we find out that rho on psi twiddle is 0. That means that any vector perpendicular to Alice's vector is an eigenvector with eigenvalue 0. The original state of Alice's spin is an eigenvector with plus 1. Conclusion, the density matrix for a pure state has one and only one non-zero eigenvalue, and it's equal to 1. What if it's not a product state? If it's not a product state, then you'll find a collection of eigenvalues. In fact, in general, there will be all of the eigenvalues in general will be non-zero of the density matrix. You can try this out for the two-spin system. Work out the density matrix of Alice's spin, the density matrix for Bob's spin, and you will find out that they're quite different. They don't have a single eigenvector which is non-zero. They have a pair of eigenvectors which are non-zero. So what we learn is that there's information in the density matrix, and in particular in the eigenvalues of the density matrix, which tell you whether there's a great deal of entanglement or not. The more eigenvectors which are non-zero, the more entangled it is. If there's only one eigenvector which is non-zero, it's not entangled at all, and Alice's half of the wave function is just that eigenvector. If they're entangled, then one finds, and the more they're entangled, the more eigenvalues you will find. And the maximum entanglement is when all the eigenvectors are equal. When all the eigenvectors are equal, all eigenvalues, when all the eigenvalues are equal, that's maximal entanglement. Take the singlet state, work out the density matrix of Alice's spin, and what you'll find is that it has two eigenvalues, each of which is a half, equal and equal to a half. So that's a test. That's the way to test whether a system does or doesn't have entanglement. Calculate its density matrix and study its eigenvalues. The maximal entanglement is when they're all equal. When they're equal to 1 over n. You can prove that, where n is the dimensionality of the space, 1 over n. Okay, that's entanglement quantified. Can even be a little more quantitative. No, let's not do that now. I'll write the more quantitative condition in the notes, and I think we've done enough enough calculation for the moment. Let's very quickly go through the connection between measurement and entanglement. There's a deep connection between measurement and entanglement. Basically, measurement is the process of entangling, of starting with a product state of what and what? A product state of a system and the apparatus. The apparatus is in a definite state to begin with, and the system is in a definite state. What state is the apparatus in? Well, the apparatus might be something which detects something or other, and if it's not detecting, you might put it in some neutral state. Some neutral state, which is the starting state, the undetected state, the neutral state of the apparatus. And now you bring the system that you're interested in right up to the apparatus. It does something to the apparatus, something happens to the system itself, and what's left over is an entangled state between the two of them. So I'll give you an example. I'm going to think of the apparatus as a very simple system with only two states. Let me find my notes here. Yeah. Yeah, my system is a spin, and my apparatus also happens to have only two states. You can think of it as another spin if you like. In fact, it could be Alice's and Bob's. But you can also think of it as a more complex system. But for simplicity, it only has two states. Here's the apparatus, and has only two states, plus, let's say 0 and 1 now. 0 is the state before the apparatus is switched on. Well, when it's switched on. When it's switched on and it's not detected anything, it always starts out in the state 0. If it's not in the state 0, give it a shove and make it, put it into the state 0. Otherwise, it's not, you know, you have to start your apparatus in some known state. Otherwise, you're not going to be able to do a measurement. So it has 0 or 1, but it starts out 0. And we have our spin. Here's a spin, and we're going to do a measurement on it. Supposing the spin is in the up state, and the apparatus, of course, begins in the 0 state. So we'll represent that by a combined ket vector. The combined ket vector is in the tensor product of the spin Hilbert space and the detector Hilbert space. Up and 0. If the spin comes in to begin with down, then you start out in the state down 0. Why? Because you start out with the detector in the neutral state. Now, I'm not going to tell you in detail what the interaction is between the detector and the spin. That could involve magnetic fields and other kinds of things causing an influence between the detector. But I am going to tell you that if you bring the spin into the detector and then take the spin out of the detector, I will tell you what state is left over. So in particular, and I'm making this up, of course, I'm making up a rule which would be a good detector, Namely, if the system starts, if the combined system starts in the state U0, then the detector feels a spin and it jumps to state 1. It goes to state U1. Nothing happens to the spin. It just activates the detector. On the other hand, if the spin is down, it doesn't activate the detector. That's my rule. So this goes to down 1. No, down 0. Down 0. And that's a very good detector of upness and downness. But now let's start with a superposition of up and down. Let's take alpha up times up plus alpha down times down. Somebody now brought us a spin in a superposition of states, in a general quantum state. But of course, the detector starts out 0. So that's the starting state. What happens after the detector acts? Well, if the state is U0, it goes to U1. So that means it goes to alpha sub U times U1 plus alpha sub down down 0. This all of a sudden has become an entangled state. It's an entangled state if it's up, if the spin is up, the detector is up, or the detector is 1. If the spin is down, the detector is 0. That is an entangled state. Why is it an entangled state? It's an entangled state because by looking at the detector, you can tell what the spin is doing. In fact, that's what a measurement is. A measurement is an interaction between a system and an apparatus that leaves the apparatus in a state that depends on the whatever it is that it's measuring about the system. So from one point of view, you can just say, well, look, this is exactly what I knew a measurement always was. It just it's just a process that leaves a record on the apparatus of what the initial state was of the spin. But from another point of view, it's the physics of a combined system, the combined system being the spin and the apparatus, which leaves them in a highly entangled state. So entangled that by looking at the detector, you can tell what the spin is. So entanglement and measurement are really the same thing. And in fact, to measure a spin, you really only need another spin. The detector here could just be a spin, and 1 and 0 could be up and down. So if we had this kind of concoction here, where exactly this happened, it would take only one spin to be a detector or an apparatus which could measure another spin. But in general, this is the nature of measurement, that it entangles systems together. It entangles, in particular, apparatus with system. Is that clear? It should be very clear. And that's all. That's one way of thinking about measurement. In this language, in which you think of the system and the apparatus together, you never speak about collapse of the wave function. You speak about the development of entanglement. If you don't want to include the apparatus into your system, then the only thing to say is that after the experiment is done, the system is either up or down, and which one do you pick? You pick the one that you record, but the one that you record is the one recorded by the apparatus. So thinking about just the system by itself, you have to have this rule that the wave function collapses. Thinking about the system plus apparatus, the same physics is described by the development of entanglement between the system and apparatus. So
in that case, for the mixed state, bottom state, what do you see on the meter of your apparatus, the 1 and the 0?
Okay, now you are another detector. All right. This is the hierarchy of detection, or the hierarchy of measurement. Here's the spin, here's the apparatus, but we're not finished. We still have to look at the apparatus. We haven't gotten anywhere until we look at the apparatus, right? All right, well, what's going to happen? Again, we're going to have to say when we look at the apparatus, we wind up collapsing the wave function to one of these two pieces of the entangled state. Or we can say include the eyeball into the system. In that case, we should have included another system here, the eyeball. And the eyeball, I don't know, how did it start? It started, it also has two states. The two states correspond to the two possible answers that the brain up there's also a brain up here. Two states of the brain. One state of the brain says, I saw the apparatus with a 0. The other state of the brain says, I saw the apparatus with a 1. If we want to include the observer as well as the apparatus, we have to include another factor here. And that factor has to depend on the state of the brain. Let's call it B naught. It starts B naught, which is the brain before it has looked at anything. And then it goes to B1 over here or B naught over here. It's now become a system which is entangled with the eye and brain. You can say, wait a minute now. We now have this entangled state. We've described it all by the quantum mechanics of the entanglement between spin and apparatus, and then later on between apparatus, spin, and eyeball. It's all been described by quantum mechanics. But you may not be satisfied. You may worry about the other fellow who comes in the room, takes a look, or asks you, what did you see? So somebody else comes in and asks you, okay, Charlie, what did you measure? And in the process, collapses the wave function of the spin apparatus. What's his name? Give him a name. No, Charlie, this is Charlie. He comes in afterwards. Wigner. Wiggy. Yeah, this is Wigner, this is Schrodinger, right? That's Wigner. So Schrodinger, and I don't know, which one of these has ears? This is the atom. This is the atom. The cat, he doesn't look at the atom, but he gets hit. Something happens. Something happens to him when the atom. So he's the detector. The cat is the detector, right? Here's Schrodinger who looks into the box, and here's Wigner who looks at Schrodinger. And there's a hierarchy here. The hierarchy, where you decide to break the hierarchy, determines at what stage you will say the wave function collapsed, if you like. I suppose at some stage you'll have to say the wave function collapsed when the last person looked at it, but you can always include that last person into the system, and then no collapse happens. But then in order to make sense out of the whole thing, again, you have to imagine some other person. So you always have to imagine a hierarchy of observation, and there is such a hierarchy of observation. The world is built like an onion. Things inside, next thing out, next thing out, next thing out, and each thing gets to observe what's in the inside of it.
What is the process whereby we move into the classical world and one of those people actually see the definite values that are superposed?
Well, I don't know. I don't think there is any sharp line. I don't think there is any sharp line. We tend to describe big systems as having little uncertainty, but I'm not sure that anything really different happens when a electron looks at another electron, or when a cat looks at an electron. I think the physics or the mathematical description, I think, is the same description. Or at least if we want to say something special happened when the cat looked, it's not well described by quantum mechanics, we have to introduce something about cats that isn't contained within quantum mechanics. And personally, I don't believe there is anything about cats which is not contained within quantum mechanics. So I'm happy with this description. What makes me happy is that it doesn't matter where you draw the line. You can draw the line in one place or the next place or the next place, and the results will be consistent. If the cat saw the spin up, Schrodinger will see the cat having seen the spin up. And Wigner will have seen Schrodinger, having seen the cat, having seen the spin up. That's what the nature of the state is. So that I find satisfying, that you don't ever have to say where you draw the line. And until you draw the line, you can put the line as far out as you like, until you draw the line, everything is described by the rules of conventional quantum mechanics.
So it seems like if you're the cat, you've definitely drawn the line.
Well, okay, yeah, I mean, yeah. Look, I think at some stage you have to decide for yourself how you think about this. I'm not going to try to push my interpretation of quantum mechanics on you, particularly since I don't know what to say about it except this. This seems to disturb a lot of people, this whole business of systems for which you can know as much as can be known and know nothing about the parts of the system. This seems to disturb people. Is it disturbing? When Feynman was asked whether he thought there was a problem about quantum mechanics, his answer was the problem is so big that he couldn't tell if there was a problem. He knew how to use it. He knew how to predict with it. He could predict anything that he wanted to predict that had an answer. And he did not expect, I'm actually speaking about myself now, but and for him, he did not expect that quantum mechanics would ever go wrong, that the rules would always be satisfied. But is there a problem because of this sense of unreality about where objectively does something happen? Does the objective death of the cat happen when the cat looks at the atom, or is it when Schrodinger looks at the cat, or is it when Wigner looks at Schrodinger? Where does the objective phenomenon happen? And maybe we're just playing with words there. Maybe we're playing with words, trying to use words in a context where they don't apply. But you have to decide that yourself. My goal is to give you the tools to be able to ask the question. And I doubt seriously that you're going to answer the question even for yourself. You'll probably come away feeling as uncomfortable about it. But you'll know why you're uncomfortable. You'll know what it is with some precision that's making you uncomfortable about it. At least I hope. At least that's my goal. All right.
In the equation you put up there with the I, forget about Schrodinger, just the I. The equation you wrote, that implies there's a correlation of 1 between the state of the system, the apparatus, the composite state, and the state of the I.
Yeah.
So would it...
In other words, the eye has become entangled with the rest of the system.
Now suppose your vision wasn't so good.
That is what you call a weak measurement. Yeah, look, no, that can happen. There can be partial entanglement for sure. I've given you a kind of idealized situation, right? Right. No, it's a serious question. People talk.
Even so good, you're not quite sure what the apparatus is saying.
Well, your eye, okay. There could be several reasons why your eye was no good. First of all, it could be that the interaction with the apparatus was simply too weak, that there wasn't enough oomph in the interaction. It wasn't that your eye was bad, there just wasn't enough coupling between the two systems, and then you only get partial information. Or it could be that your eye is bad because you have cataracts, let's say. All right. In that case, the eye did a measurement. It became entangled with the system completely. It's just the connection between the stuff in your eye and your brain wasn't good enough to send the signal back to your brain. So the correlation happened, but it was a bit messy.
Is that a detector efficiency problem?
Sometimes it's a detector efficiency problem, and sometimes it's a problem. Well, detector efficiency could have to do with the strength of interaction with the system, or it could just be that it's too hard to get the signal out. So I'm not sure what detector efficiency really means, but I could think of several things. One is the signal is there and imprinted itself on the system, and you personally have a hard time getting it out. The other is that the interaction was not strong enough to really establish a full entanglement between these systems. Both can happen.
What about a lip reader watching a dubbed movie?
Right.
So would it affect the litter detector?
You can think of all sorts of variants on this.
Would it affect a litter detector?
What's that?
Let's say there was a bad detector in between that got entangled, and then I had a perfectly good detector later on. Would it affect the measurement of that?
Well, I think this probably, I guess the weakest link is where you, yeah. All right, let's talk about locality. Let's talk about locality and entanglement, which is really where people get hung up. I mean, and the villain, the arch villain here, who really tangled things badly, was Einstein. Einstein, and not that he asked a question, of course, he asked a wonderful question about entangled systems, really our understanding of entanglement, and much of what we think about it and our curiosity about it goes back to Einstein's question in 1933, who was very much puzzled by this idea that you could have a system about which you knew everything and yet you knew nothing about the components of it. And he wrote a paper simply complaining about it. I don't know if he was the first one to notice the phenomenon of entanglement. I have a feeling not. He was the first one to get really exercised by it and say something is very peculiar here. That I find quite okay. He then used the term, what was the term again? Spooky action at a distance. And that got everybody confused afterwards, because Einstein knew exactly what action at a distance meant, and it didn't mean what he meant when he was using it in this context. Action at a distance literally means forces between systems at a distance, the ability to affect the outcome of an experiment at one place by doing something at another place. Action at a distance, the Coulomb force between electrons. Now, of course, in the real world, it's not action at a distance. But in Newton's world, well, Newton didn't know about electrons. Newton knew about gravity. In Newton's world, the gravitational interaction was action at a distance. And the meaning of that, from our point of view, is that if something came along and gave the sun a sudden shove, we would know it instantly, for the simple reason that the orbit of the Earth would instantly react to the change in position of the sun. The force on the Earth would instantly react. And so every measurement of everything that you might want to measure would be, to some extent or another, modified by the sudden change in the orbit of the sun. That's what action at a distance meant. The ability, if you like, to send a signal. By shoving the sun, you're sending a signal to Earth, and you're sending it instantaneously if there's action at a distance. Einstein must have known, I am certain that he knew, that entanglement did not entail action at a distance in that sense. What one can do, what one can work out, is supposing you start, I'll give you something you can try to play with and see if you can work it out. Supposing you start with a system which is a two-part system. It has a wave function psi of A and B, and from that system you can construct a density matrix. Here's Alice and Bob. You can construct a density matrix rho for Alice. That density matrix contains every possible statistical prediction that Alice can ever make for her subsystem A. Now let's imagine that Alice and Bob took their subsystems. Alice went to a distant planet. Bob stayed in Palo Alto. And they're very far from one another, so far that it would take light 4 years to get from one place to another. Bob does an experiment That means, now this is this could be an entangled state. This is not a non-entangled state. Bob does an experiment, and that has an effect on his half of the system here, but it has no effect whatever on Alice's density matrix. Perhaps I can prove that. I'm not going to prove that tonight. It's not too hard to prove that any physically allowable change in this wave function, which only involves Bob half of it, the process of interacting with some other system or whatever it is, Bob gives his electron a knock, whatever he does to it, he will not have any effect on Alice's density matrix. That's the way quantum mechanics is really put together. And the implication is that anything that Bob does suddenly at a fixed instant of time will not have any effect on any prediction or the success of any prediction. It will have no effect on the statistical probabilities of Alice measuring anything about A. It just will not. So in that sense, it was impossible for Bob to send a message to Alice suddenly. Now, of course, he can do an experiment on his subsystem, and after he's done the experiment, he can then send a telegram to Alice far away in the standard way that you send messages and tell her what the result. So again, this is an entangled state. It could be up, down, minus down, up. When Bob does a measurement on his spin, it has no effect on Alice's density matrix. He can then send Alice a message and say, look, I saw down. And Alice will say, yeah, that's because I saw up. They were correlated. I thought they were correlated, and you just confirmed that. I measured up a few months ago, and in fact, I'm now getting your telegram, and it tells me that you got down, and that's consistent. Everything is fine. Nobody sent any message faster than the speed of light. The mere fact that when Bob measures his variable, he instantly knows something about Alice's is no source of anxiety for locality. This would happen for nickels and dimes for perfectly classical systems. The peculiarity is different than that. The peculiarity has to do with this idea that you can know everything about a system and yet know nothing about its parts. What is it then if locality, the standard physicist definition of locality, is not at risk, and you can't send signals faster? What is it that Einstein meant, and what did Bell mean, and what did all the other people who talk about these things mean when they said entanglement entails a degree of non-locality? So I'll try to explain to you by imagining a game. Yeah.
If Bob made a measurement and Alice did not, and Bob sent Alice a message after his measurement, would that information alone be enough to change Alice's density matrix?
Be enough to what?
To change Alice's density matrix.
Oh yeah. If Bob sends a real message and Alice hasn't looked yet. Okay, so let's say Alice has not looked. She doesn't know anything yet. And as far as she's concerned, the density matrix is consistent with that and basically tells her nothing. That's a density matrix which hasn't got very much information in it about her spin. And then she gets a telegram from Bob saying, my spin was up. As far as Alice is concerned, that collapses her density matrix and tells her her spin is down. So if thereafter, she will use a density matrix which says that her spin is down. So yes, once a message has had time to go between them, yes, then she will know something that she didn't know before, and she will therefore update her density matrix. But that will only take place after there's been sufficient time for the signal to propagate. Yeah.
if I understand correctly, the statements that we're making here are about expected values of these
Yes.
experiments, right?
Yes.
But when you realize it once, you're actually not going to get the expected value. You're going to get, but this also holds for every value, not just the expected values, right?
No, expected or expectation values, or whatever you want to call them, average values. If you know the average values of all variables, you don't need to know. Okay. Supposing we have one variable that we're interested in. Let's call it L again. If we know the average value of L, the average value of L squared, the average value of L cubed, ... we know the whole probability distribution of L. This is called knowing the moments, all of the moments of a probability distribution. If we know all the expectation values of L, L squared, L cubed, actually for a single spin you only need the spin and the spin squared, then you know the full probability distribution. Once you know the full probability distribution, that's all you can know. So, knowing a full set of expectation values like this is knowing everything that Alice can know about the system.
But the actual realization of the experiment when it happens once.
Oh, that's right. Yes.
So
Yeah.
one person
Yeah.
measures
No.
up, the other person measures down.
Yeah.
Then
That's right.
they still are guaranteed to be opposite, right?
They are. They're guaranteed to be opposite. Yes.
So I guess that.
But Alice doesn't update her information about it until she gets it. Before Alice gets the information, as far as she knows, it's half a half. But let's try to do a little better. Alice and Bob are now going to each have many spins. All right? So Charlie is going to give each of them many entangled pairs. All right? So Alice has spin number 1, and Bob has his spin number 1, and they are in the relationship of being entangled. Also, Alice has spin number 2, which is not entangled with spin number 1, but it happens to be entangled with Bob's spin number 2. Charlie gave him a whole series of these. So that they can do statistical experiments and collect statistics. When they've collected statistics, they will discover that every time Bob is up, Alice is down. Every time Bob is down, Alice is up. But now they can do a lot more than that. They can, let's see, what's a good example for what can be done? Yeah, right, good. Bob does all of his experiments here at some instant of time and finds out every one of these, finds out exactly what every one of them is doing. Does that convey any information at all to Alice about which she knows that just about half of them are up and half of them are down? Bob goes and makes his measurement. He does his measurement on every single one of them. Does Alice know anything afterward that she didn't know before? No. Does anything surprising happen when she measures these things? Does the statistics of these things over here in any way change because Bob measured these things? No. There will be no statistical difference. Bob can do his measurement, throw his measurement in the waste paper basket, but he's measured every single one of these. It has no influence at all on what Alice measures. But if Bob sends a message to Alice before she does her measurement and says, spin 1 came out plus, spin 2 came out minus, blah, 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 then instantly Alice knows everything about these. In fact, he could say, sigma z equals plus 1. But he decided over here not to measure sigma z. He said, I'm going to measure sigma x over here, minus 1. And over here, he measures sigma y equals plus 1. Having made these measurements, without informing Alice in any way, does nothing whatever to the statistics of her measurements. But if he now sends them, she can now decide. She can decide to measure anything she wants. But if she decides to measure sigma z because she knew that Bob got plus 1 here, and sigma x for this one, and sigma y for this one, we'll find that in every case that they're opposite.
You keep saying Bob sends the message. I just want to make sure I understand.
Yeah, he sent a telegram.
It's not him sending it, it's her receiving it that matters.
Well, of course, yes. Right. No, the important point is that it takes time to send a message. Yeah. What? I missed. Okay. Well, yes, that is a problem.
I don't know if this captures, it seems like this feeling about spooky action at a distance comes not from thinking externally about Bob and Alice doing measurements, but almost thinking about inside the system, like there are these two separate entities.
Well, I will try to give you a precise definition. All right. Now, there is a theorem lurking here. I don't know that the theorem has ever been discussed in the computer science community. It's a kind of computer science theorem. Whether anybody has actually discussed it in the language I'm going to tell you now, I don't know. And I don't really quite know how to formulate it as a theorem. I've never tried. But I think I can capture the essence of what this theorem would say, if only the theorem could be made precise. We have 10 minutes to try to do this. If we go over a little bit, we'll do that. Here's the game I want to play. I'm going to write a computer program. My computer has a screen, okay, it has a screen, and all the usual things that computers have. Over here on the screen is a little black box, and that little black box is called spin. You can't see inside it, but there's something in it. And in here is apparatus A. And apparatus A, you can see what it's doing and so forth. Right? It's got a 0, it can measure 0 or 1. Now, here's the game. The memory stores two things. The memory stores information about the spin. This is a completely classical computer. The game we're going to play is I'm going to fool you into thinking there's really a quantum mechanical system in here. How are we going to do that? We're going to do it by I'm going to write a computer program which completely simulates the classical computer program that completely simulates what happens when an apparatus looks at a spin. Okay, so here's the way it's going to go. We're going to start, just for convenience, we'll start with the spin in a known state. Right? So the apparatus or the computer program, it's not important, but the computer program, let's say it starts out with the spin up or whatever it's doing. Right? The apparatus can either read 0 or 1. There's a button over here in this, there's a button over here that you touch, and that button is M. Means you measure, means measurement. So when you touch that button over here, the apparatus measures the spin. The computer records two things. It records the state vector of the spin. How does it do that? By providing two complex numbers. Stored in the computer are two complex numbers, alpha up and alpha down, subject to the constraint that alpha star alpha plus alpha star alpha is equal to 1. So it stores an information which is equivalent to the state vector of the spin. And the other thing it stores is the direction that you point the apparatus. You can move the apparatus around by playing with the computer. Not move it around, but you can reorient it in any direction that you like. You start with a spin up. Now, this spin might be interacting with a magnetic field or whatever's happening to it. The computer solves the Schrodinger equation. In solving the Schrodinger equation for the spin, that means it updates the state of the spin. You start with a particular state, doesn't matter what it is, and after a time t, it updates the spin, it updates the state, so the computer now knows what alpha is after a certain time has elapsed. Then you punch the measure button. And the computer takes the state, turns it into a pair of probabilities, alpha star alpha up, alpha star alpha down, The computer now knows the probability for up and down, and it also has a random number generator. Random number generators are a dime a dozen, and they work very well. With the random number generator, it then takes the probabilities alpha up and alpha down and spits out a number plus or minus 1 with probability alpha star alpha and alpha star alpha. So it just simulates the quantum mechanics by having a random number generator that either spits out +1 or -1, but with a probability that's given by alpha star alpha. All right? But then the computer then, whatever the answer is, whatever the answer that the apparatus spit out, the computer then updates once again the state of the spin and says it is in the state that the apparatus measured. So if the apparatus spits out +1 along some axis, you get to turn the apparatus, but because when you get to turn the apparatus, you have to do a slightly complicated calculation to find out what the statistics are. But once you've done it, whatever the answer is, the computer goes back and updates the state of the spin to make it consistent with what the apparatus measured. You can do this. You can try to write a program. This is a program that could be written. It's probably not even terribly complicated. And if you only got to look at the measuring button, decide to measure, and look at the outcome, you would get everything exactly equivalent, to the extent that a random number generator can be a good, faithful random number generator. You would completely simulate the quantum mechanics of the system. The lesson is that quantum mechanics can be a special case of classical physics. So what's going on? If quantum mechanics can be a special case of classical mechanics, what's all this confusion about quantum mechanics being logically different? All right. Now we want to play the same game with a pair of spins.
Just one question. You said that you're trying to say quantum mechanics is a special case of classical, but I thought in classical everything was deterministic and introducing a probability.
Okay, but it's yeah. But this is a classical computer, and it's using a classical number generator, a classical random number generator. All right. So you do have to add in, but the difference between quantum mechanics and classical mechanics isn't randomness. You can generate all sorts of random number generators that would easily fool you into thinking they were really random. Of course, any real random number generator, the numbers come from somewheres, so they're not strictly random. But you can sure make a random number generator that would fool anybody. So, yeah, you can build a computer program to simulate the quantum mechanics, basically of any system that you like, by the same method. Okay, but now supposing you wanted to simulate a system consisting of 2 electrons. There's 2 electrons, 2 boxes here, and you wanted to do it with 2 computers. And in the process of taking the electrons apart from each other, so as to ask this question about, you want to take the computers, you want to encode the information about Alice's spin in one computer and Bob's spin in the other computer, physically separate them, and ask, can these computers simulate quantum mechanics? So I'll tell you what the answer is. As long as the spins are in a product state, as long as they start in a product state and they don't interact with each other and therefore stay in a product state, then you can do it. You can put all of the information about Bob's spin in here, all the information about Alice's spin in here. Likewise, you can have Bob's apparatus over here. You can have Alice's apparatus over here, little black boxes. And it's just basically 2 identical versions of what I said before. You can take the computers, physically separate them, do experiments on each one, and they will completely agree with the results of quantum mechanics, because if they're in a product state, one doesn't care about the other. But then you say, what if I wanted to put these 2 spins in an entangled state? Well, first of all, to put them in an entangled state, you cannot do it without bringing the computers together. bringing the computers together so that they talk to each other. You can record in the combined computer system, now that they're brought together, how many numbers does it take to specify the state of a two-spin system? 6. So you record 6 numbers in the computer here. 6 numbers are recorded in the computer, and some numbers to reflect the orientations of various apparatuses that you might conceive of. And then you try to split the computer into 2, keeping Alice's information in here and Bob's information in here, separate them, and try to simulate the quantum mechanics of the entangled system. Bell's theorem is what tells you that you cannot do this unless there are instantaneous action at a distance phenomena taking place between the wires between the computer, so to speak. Hidden wires that have to be part of the system connecting the computers together. You cannot simulate the quantum mechanics with a classical computer system. You can't simulate the quantum mechanics of an entangled system unless it's really just one computer. Really, one computer means that signals can be transmitted back and forth basically instantly. That's what Bell's theorem really says. Now, is this a form of non-locality? Well, you might think that if you really have to have these wires there to simulate quantum mechanics, then why can't you send an instantaneous message through these wires? Of course you can, but not if you only allow yourself to do the things which quantum mechanics permits. For example, there are things that quantum mechanics doesn't permit. It doesn't allow you to measure the x and y component of a spin simultaneously. All kinds of things that it does not permit you to do because they correspond to non-commuting operators. If you restrict yourself to the measurements which quantum mechanics allows you to do on either one of these or any combination of them, then it's a very magical and special fact that you cannot send information faster than the speed of light. You cannot send information instantaneously by this computer setup.
What if you assign not probabilities, but conditional probabilities?
Doesn't matter. Doesn't matter. If you want to simulate a quantum system with a classical system of computers, and you want to study entangled systems, the computers have to be able to communicate with each other instantaneously. That's the content of Bell's theorem. Now, does that mean that there's any action, spooky action at a distance, or does it just mean that you've gotten yourself into trouble by trying to simulate quantum mechanics with classical mechanics? My view is that you've gotten yourself into trouble by trying to simulate something which just doesn't want to be described by a classical computer system, and it's a deep and interesting fact about quantum mechanics. Einstein's view was that this is basically evidence that the description is incomplete and that there are other variables of the system, and Bell's conclusion was those other variables have to be hidden wires that connect distant places. So you can take it for however you see it yourself, yes.
So if you had a quantum computer there, and let's say when you had the states,
If you had a quantum computer, you could do it.
and you separated it,
Yeah.
right? Now, when you observe Bob's computer, now you know something about Alice's, right? But you can't really still send
It's the same problem.
Right.
But look, all a quantum computer is an electron in this computer and an electron, that's all it is.
Right, but they
It's
were
just a quantum system. Right, it's just a true quantum system, a quantum system in each one of these which has been entangled. That's all a quantum computer is. It's a quantum mechanical system which can reflect the logical structures of quantum mechanics, and the way you make it is by actually making a pair of entangled electrons in there. Something real has been entangled between them, and it can't be simulated by a fake computer program unless the computer has this property of. Yeah.
But you still have the problem of transmitting that information somehow.
Oh, no, you have, sure, right. Yeah.
You could sort of hack this problem away if you, using your analogy, we said that there are pseudo-random generators who are synchronized, so there are actually, not.
Yeah.
Sure. Bill Stevenson proved that you couldn't do that.
Yeah, no, but what you can't do is synchronize them in advance and then not let them interact with each other. That won't do it. The random number generators have to be such that what this one measures responds to what that one measured.
Like for example, what I meant to say, maybe I didn't explain it very well, is that the random number generators are synchronized at the beginning, and whenever you measure, because they're synchronized, they will always generate up and down, reversed.
No, they lose the memory. Random
They
numbers
lose what?
lose the memory of earlier state.
No, it's simply not enough. This is what the theorem says. It is not enough to synchronize them in advance and then take them apart. They've got to continue to interact with each other. That's what it says. That they must continue to interact with each other and feed information back and forth. Yeah.
I think, if
Or somebody.
oh, sorry.
Bill, the problem with the delayed choice is if you put a filter in Bob's instrument, then instantaneously Alice's correlation is affected, even if she is 4 light years away. That's actually a distance.
I told you everything I know about it, and what I know about it is that there's nothing Bob can do which can influence the statistics of Alice's measurements without sending her a measure.
You have to depend instantaneously on the setting of the distant instrument.
Okay.
Yeah,
All right. One more minute. Two more questions.
forget action at a distance of 2 separate computers. I just find it interesting that if you have a single computer, are you saying you can actually classically simulate quantum mechanics?
Yes. You can classically simulate quantum mechanics, but you basically have to do it within a single computer where all parts of it speak to every other part. You cannot physically take them apart the way you would want to take the quantum systems apart.
I'm a little confused on being able to measure the system as a whole versus the parts. It seems like you're measuring the parts of the system. Bob's making a measurement of the part. Alice is making a measurement of the part. But I think one of the statements you made was that entangled systems, you don't measure the entire system.
No. No. In an entangled system, Bob can do his measurements, Alice can do her measurements. But there are other things that can be measured besides just the things that Alice would measure on her system or the things that Bob would measure. For example, neither Bob nor Alice by themselves can measure sigma x times tau x. It takes both of them to do it. It takes both detectors, it takes both apparatuses to make a measurement of sigma x times tau x. This is something that you cannot measure. Now you can measure it with 2 apparatuses. The question is, are there any things that you could measure that you couldn't measure even with those 2 apparatuses? And yes, there are. Sigma x tau x plus sigma y tau y plus sigma z tau z is something that cannot even be measured by using both apparatuses. It takes a new kind of apparatus, which is not a combination of Alice's and Bob's original apparatuses, which each measure a Bob thing and an Alice thing.
So Bob cannot measure the entanglement. Yes.
Nobody can measure entanglement.
You have to talk to Alice to know that there's an entanglement involved in the system.
No, Bob can discover that he's got, if he has, nobody can do anything with one event. But if we have a whole replication, like I described over here, where did I describe it? Where we have many replicas of the same thing, then Bob can discover the fact that his state is entangled with something. And the way he does it is he says, let me search around for a direction in space for which the spins are definitely aligned in some direction. Here's what he knows. He knows that all the systems were prepared in the same way. They're all identical. Each pair is identical to each other pair is identical to each other pair. And he's wondering, could each one of these be in a product state? Same product state for this one, same product state for that one, same product state for that one. If they're in a product state, then Bob can search around. He's got enough versions of it, enough trials, that he can go on and on with experiments forever. And he can search around for a direction where, when he measures the spin, his spin, he always discovers that it's up. Now, the first time he may be in the wrong direction and he'll find down. Next time he may find up, he'll try it again. It'll be down, wrong direction, and he keeps searching around. If it's a product state, he will eventually find a direction where the spin will continue to be up, 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 up after he's found it. If it's an entangled state, no matter what direction he measures, he will always find the spins are random. Okay, that's the character of it. Good.
And that's on separate measurements, right?
Hmm?
On separate discrete measurements, not the measurement of the same thing.
No, you've got to have an ensemble of identical systems to do anything like this. You just prepare each one the same way. You do an experiment, and he doesn't care about Alice. He's just going to measure his spin along some axis. Another axis, until he finds one where he keeps repetitively getting the same answer. And then he says, that's the direction that spin is polarized. And then he keeps doing it and finds consistency. He'll never find that unless it's a product state. So it's pretty interesting stuff. Hard stuff.
For more, please visit us at stanford.edu.